Hello and welcome to our examination of an existing coffee grinder blade design.
I am Jack Highland.
And my name is Jake Delgado. The goal of this project is to construct a virtual model of an existing product and make design changes to improve the product's material stresses. Today we are comparing the performance of the existing blade design against a modified version. Of special interest here is whether the blade design can be improved while reducing stresses in the blade material. For the purposes of this study, the blade material was assumed to be stainless steel. Because we wanted to minimize the number of design change variables, we used stainless steel for the redesigned blade as well. Visible on the left is a photo of the actual coffee grinder used, and on the right is the SolidWorks model created for the evaluation. The SolidWorks geometry was then imported into ANSYS to analyze blade performance. Shown here is an exploded view of the original design. The design was replicated in SolidWorks by carefully measuring the physical parts to create several parts. For the clear portions of the lid, we selected polycarbonate as the material which is common for high-impact applications where the material must be transparent. The blade assembly contains a metal portion that appears to be brass, so that was used for the blade support material. All the black plastic portions of the assembly were assumed to be ABS plastic. Finally, all the exterior steel portions of the grinder and lid were assumed to be stainless steel sheet. The blade to be redesigned is the middle component of the 5 shown. In the actual design, the blade is not a removable part. The physical blade to shaft attachment is obscured by the plastic molded around the 2 parts. For this analysis, an interface between the 2 parts was devised for positive attachment. If the actual attachment is different, the stresses in the blade observed at the shaft blade interface would be affected. In this enlarged view of the 2 blade designs side by side, the plastic surrounding the blade shaft interface is clearly visible. On the left is the original blade design with a blunt edge in the direction of rotation. On the right is the modified version with tapered edges in the direction of travel. We expected the modified version would cut through the beans with less effort, thus reducing the stress in the blade material.
We selected the point on the leading edge of the blade farthest from the axis of rotation as the radius where the force is applied, as this would give us the maximum force that the blade would experience with the given load. The radius was determined to be 33 millimeters. We filled the cup full of coffee beans, and the weight of the beans came out to 45 grams. We decided that not all of the weight would be in contact with the blades at any given time. Therefore, we conservatively decided that only 20 grams would be in contact with the blades. In ANSYS, we would only be applying the analysis to half of the blades, so we used 10 grams for the calculations. The blades on the coffee grinder spin at 3,600 RPM. We calculated the angular velocity to be 377 radians per second. Multiplying the radius of the blade by the angular velocity, the linear velocity was determined to be about 12,500 millimeters per second. Applying it to the force equation shown, we determined that the force of the coffee beans would exert on half of the blade would be 47 newtons. We cut the blade model in half to be able to generate a better mesh and analysis in ANSYS. We fixed the faces of the blade which would mate with the output shaft on the motor. We then applied the force to the whole leading edge of the blade, as the interaction with the beans would be more of a medium rather than a single force applied to a point. In this slide, you can see the analysis of the original blade. For the analysis, we originally used the default settings to generate the mesh. We decided that the results did not give a good representation of the stresses on the part. We increased the mesh resolution to 7 and created a mesh with 33,223 nodes and 19,089 elements. With the chosen stainless steel material, it had a Young's modulus of 1.93 times 10 to the 5th megapascals, a Poisson's ratio of 0.31, and a yield strength of 207 megapascals. The total deformation was 0.0201 millimeters, and the von Mises stress was 50.6 megapascals. In ANSYS, we probed the maximum and minimum locations of both the total displacement and von Mises stress. The maximum displacement of the original blade was at the very top of the blade. The maximum stress was on the bottom of the blade in the corner of the mating faces closest to the leading edge. These locations were to be expected. In the analysis of the modified blade, the mesh generated had 31,767 nodes and 18,075 elements. In this slide, you can see the total deformation and von Mises stress of the modified blade. The total deformation was 0.0106 millimeters, and the stress was 28.84 megapascals. The total deformation on this modified part was decreased by 53% because of the decrease in frontal area that the force was applied. The von Mises stress also decreased by 57%, which resulted in a lower stress concentration at the mating faces.
In this view, the motion of the blade can be seen in the grinder. During operation, the cup is filled with beans as shown, installed on the base, and the translucent cover placed over the cup. The blade rotates in the clockwise direction as viewed from above at a single speed to grind the contents of the cup. The grinder stops when the button on the top of the clear cover is released. After the stresses in the original blade were analyzed using ANSYS FEA, the blade was modified to have a tapered leading edge. This change was made to observe the effect of reducing the area of the material directly exposed to impact with the contents of the cup. As expected, the revised design resulted in reduced stresses in the blade material. In conclusion, the blunt edge blade experiences greater stress than deformation due to the greater surface area exposed to the material being ground. This behavior was apparent in the high stresses at the blade shaft interface where the metal of the blade is thinnest, as well as the greater deformation at the tip of the blade. The stress concentration area is naturally the highest stress location due to the moment around the center of the blade caused by the applied load. It should be noted, however, the stresses observed in each case were well under the maximum yield strength of 207 megapascals for stainless steel, given by ANSYS material properties. Finally, the tapered blade design would likely produce a finer grind more quickly due to the smaller edge profile. This would result in the blade cutting through the material to be ground rather than pulverizing it with a blunt face. Overall, the updated blade design with tapered leading edges is an improvement to the design. Thank you for watching.